Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class as a supplement. I'm putting it online in case it would be helpful to others as well. This is video 2 of what our textbook calls section 3.1, which is a lesson all about the definition of derivative. There are printable notes that you can access. You can find them in the description of the first video for this section. In today's video, what we'll be talking about is the alternate definition of derivative. So let's just jump right back into it. We are right here, and this is something that's not in the guided notes. However, I just wanted to start here to remind you that this is something that we talked about in video 1, where we just had a curve. That's what you're seeing with the blue part of the graph. And we defined 2 points on the curve, and then we drew a secant line through those 2 points. We define the ordered pairs of those points to be x, f of x, and x plus h, f of x plus h. And we wrote the slope of the secant line with those ordered pairs. And then what we did was we turned it into the slope of a tangent line by adding a limit to that slope formula. Okay, again, that's all from video 1, so I'm not going to write all of that out again. I just wanted to start there because what we're going to do today is talk about another way to look at the definition of derivative, and it really is just a different way to label the points of your secant line. And what you'll see then is because of the different way that we label the points, we have a slightly different limit. So let's read it, and then I'll explain it graphically. All right, so the derivative of function f at the point where x equals a is the limit f prime of a equal to the limit as x approaches a of f of x minus f of a divided by x minus a. I think that the one thing I really like about this definition is that it really holds the slope formula there. Whereas with the h approaching 0 definition, you just see the h in the denominator, and so sometimes students lose sight of the fact that that is a slope formula. Here you can definitely see the y2 minus y1 over x2 minus x1 form in your slope expression, and then you just have that additional limit piece in front of that. Again, as I said, I want to explain to you graphically what that means, and this should be in the printable notes. So if you're following along with the notes packet, you should have this as a blank set of axes, I believe, like before. And so again, what you would want to do is draw the blue curve, and then let me get my pen here. Take 2 points on that blue curve, about here and here, and draw a line through those 2 points, and that again is called a secant line. All right, now the difference today with what we're going to do is we're going to just label these points a little bit differently. In the first video, we labeled this as x and this as x plus h, the x coordinates. Today, we will label this x coordinate as a and this x coordinate as x. We're not going to label the distance between them today. Last time we labeled that as h. Okay, we're just going to leave it again as a and x. That would make, if we call this y equals f of x, that would make this y coordinate f of a and this y coordinate f of x. And so just like I did yesterday or whatever day, I'm going to, in the first video, I should say, I'm going to label the ordered pairs of these points. I have a, f of a is one of the ordered pairs, and I have x, f of x is the other ordered pair. And now I'm going to write the slope of the secant line between those 2 points. And that would be f of x minus f of a, right? That's y2 minus y1 over x minus a. Right, so again, that's just writing the slope formula given 2 points. Now, again, what we want to do is make that formula into the formula for the slope at just 1 point, and we're going to label it at this point. And that will find the slope of what we call the tangent line. The tangent line is the line that hits the curve at just 1 point. So I did fairly well with this, drawing this line last time, which means I'm not going to do well today, everybody, just to warn you. All right, let's see if I can do this. I'm going to draw a line. Oh my gosh. I think I did it. I'll extend it, make it nice and long. All right, that's pretty good again. Yay, I'm getting better at this. And let's label that the tangent line. And now again, what we want to do, just like we did in the first video, is we want to adjust the slope formula that we have here to be the slope formula for the tangent line. And that only involves one step. It involves the limit, right? We need to have a limit in here that says, let's take those 2 points that we defined and make them into just 1 point. Okay, that's the definition of a derivative. And to do that, what we need to put in front of all of this is the limit as x approaches a. We want to take this point and get it closer and closer and closer to being the same point as a comma f of a. And we can just do that with a nice little limit here. Let's write the limit as x approaches a of f of x minus f of a over x minus a. And there you have it. There's the definition of a derivative. This is called, again, the alternate definition of derivative, and it does the same thing that the original definition as h approaches 0 did for us in the first video. Okay, so what I usually tell my students at this point is that you don't need to memorize, I hate that, you don't need to memorize both of these formulas and know how to use them. I do suggest that you practice it for a little bit just to see if you like it better. And then if I tell you to take a derivative using a definition, you need to decide whether you want to use the limit as h approaches 0 formula that we discussed in the first video, or the alternate definition, which we just call the limit as x approaches a formula. So what I want to do in this next example is just show you what this formula looks like. And it's going to be the same thing that we did in the examples in the first video. So we have 3 parts to example 2. There's an A, B, C. And what we'll be doing is finding the derivative of the functions at the given points, this time just using the alternate definition of derivative. Okay, so let's go. Let's go. All right, just like before. Oh no. Okay, here's a difference. I almost made a boo-boo here. All right. Last time, if you watched the first video, I said this letter A, you can change it to an X if you would like, and you can still do that, but it might actually make sense to leave it as an A because the alternate definition has this A in it. Do you see that? Okay, so I am just going to leave this as an A value, and I'm just going to call it my A that I need for the formula. But like before, really all I'm doing here is I'm setting up 2 ordered pairs. I have an x coordinate of 1, comma, sub that into the function. So I'm thinking about right now, 1 squared plus 3 times 1, that's 4. That would be my y coordinate. You can still even label this x1, y1 if you like that. All right, now the second ordered pair, if you remember what we did in the original definition, we took this x coordinate and we added h. So this would have been a 1 plus h. That's not the case for the alternate definition. And this is actually where some students kind of like it. They're like, oh, it's that easy. All we're going to do here is we're going to label the second x coordinate as just x. That's it. Comma, and then this, look at this equation. Look at it for what it's saying to you. It's saying y is x squared plus 3. So the y coordinate is x squared plus, oh man. I said plus 3 and it's plus 3x, and then I wrote x cubed. Sorry, all right. X squared plus 3x, that's the y coordinate. Okay, and you can label that x2, y2, if you like that. And now we are doing the derivative, which again, you have all sorts of notations out here. I'm just going to use y prime, which by the way, that's called the Lagrange notation. So just a little fact there. All right, and I'm going to do y2 minus y1 over x2, which is x, minus x1, which is 1. And finally, let's put that limit out in front, and here's what your limit is. It is the limit as x approaches this value, 1. Okay, so that's the major difference between the original definition that we saw in the first video and the alternate definition, is that you are defining your points in such a, in a manner that you are not going to have a limit as h goes to 0. You're going to have a limit as x approaches whatever value you're trying to find your derivative at. Okay, and now our goal, just as before, was to evaluate this limit. We want to eventually be able to sub 1 in for x. We're not going to do that at this point because we would get 0 over 0. So we need to work on some sort of manipulation technique. I would say some factoring here, some algebraic manipulation in order to do that. Okay, can this be factored? Good news, it can. Let's bring along our limit. So this is actually at the point where I tell my students, if you like the alternate definition for some of these, you are going to need to be good at factoring. And they're like, oh, never mind. All right, this one's not bad though, right? What do we have here? X plus 4 and x minus 1 would be the factors of x squared plus 3x minus 4, right? Yep, okay. And then we have this happen. This is like the good stuff happening, right? So now we are doing the limit as x approaches 1 of just x plus 4, and we can sub 1 into that and get a derivative of 5. Yay! Okay, so sometimes I see students say, wow, that just seems a little bit easier than the H formula. Others say, nope, I am well on my way to understanding the H formula. I am not going to touch this alternate. And, then I usually get the question from students. They say, well, does it matter? Like, is there going to be a point where we have to use one or the other? And I tell them, well, for certain functions, the type of definition you use will be easier. So for example, I think that whenever you're differentiating, and you're going to see this today, whenever you're differentiating a square root function, I like the alternate definition better. It doesn't actually make that much of a difference, but I just prefer it. When I go to prove the other derivatives of functions like trig functions and exponential and logarithmic, not logarithmic, but the exponential functions, we use the original definition. So it's, it's all about what seems easier and what you need to do, which is really hard to teach. It's just sort of something that has to come with experience. Okay. Oh, let's do what we did in the last video as well. Again, this is not something that's required, but I just kind of like it to remind you of what we just did here. We said for y equals x squared plus 3x at x equals 1, y prime is equal to 5. That's what we just found. So that's just a little reminder also that there is that shortcut out there, rules that'll quickly get you this answer from doing something here with this point. And that's something that we're moving toward. I promise we're getting there. All right, let's move on to part B. And what I like about part B is that you saw this exact example in the first video with the original definition. So here you're seeing it again. but you're seeing it now with the alternate definition, so you can like side by side compare them and decide which one looks easier and makes more sense to you. So I'll remind you that we already know the answer. We know it is -1/9 because we got it in example 1C. Okay, and just to remind you, here's what we did. Now let's do it again with the alternate definition. So I'm going to set up the first ordered pair as 3, 1/3 again. The second ordered pair, remember, this is like kind of easy, right? It's just x, 1/x. No h here with the alternate definition. Then my derivative will come from, let's just put that limit there at the beginning, the limit as x approaches 3, because I'm using the alternate, that is the limit I would set up, of y2 minus y1 over x2 minus x1. Okay, so now what? Well, let's do that thing that we did in the example 1C. Bring along your limit, where we can eliminate this complex fraction if we just take each part. Watch what I'm doing. I'm taking each part of the difference of the fractions that are being subtracted in this overall numerator, and I'm going to put the x minus 3 that's down here in each of those parts, like that. Okay, that's not getting a common denominator, by the way. Like, if you're wondering, well, why isn't she multiplying the numerator by x minus 3? I'm just like, this is a weird way to say it, but I'm just kind of shoving that x minus 3, up in here right now, because it's down here, and we can just do that. Sometimes I call it in my class, this is embarrassing. Should I even do this? Joey, I remember your face. Joey, you have to watch this video, because now I just called you out by name. I called this the method. You can just put it together. I'm talking about this right here. All right. This is embarrassing. I'm going to move on. So now we're ready to get a common denominator where we are multiplying the first fraction by 3/3, because we need this factor of 3 that's in this denominator to be over in this denominator. And we're multiplying this fraction by x over x, because we need this factor of x to be over here. I'm going to take this work down here. So let's bring along our limit. And again, this fraction is getting multiplied by 3/3. So it will be 3 over 3x times the quantity x minus 3. Minus, this fraction needs to get multiplied by x. So it will be x over, let's just put it in the same order, 3x over x minus 3. So that's an algebra step that I know sometimes students struggle with. You just sort of have to practice it and get used to it. You need to be able to do a common denominator. Bring along the limit. And we can now combine these because we have the common denominator of 3x times the quantity x minus 3. Okay. So now it would be so tempting to do this, right? Cancel 3 minus x and x minus 3. And you can do that, but you got to keep in mind the 3 minus x and x minus 3 are different by a factor of -1. Subtraction is not commutative like that. If it was 3 plus x and x plus 3, sure, but it's subtraction there. So I'm going to do this, which some people would say, I don't really need to show this step, but I like to show it just so that we're clear. Especially when we're starting out and there's just so much stuff, right? You can factor out a -1 from this. That'll make a -3 and a positive x. And then I just change the order of them. If I have a -3 and a plus x, that's the same as x minus 3. And now I can easily divide those out, because that is 1 there. And so I'm left with the limit as x approaches 3 of -1 over 3x. I can sub 3 in for the x at this point. And yay, we got the answer that we wanted to get, which was -1/9. Okay, so again, you have seen this example done with both the original definition and now the alternate definition, so you can decide which one makes most sense to you. Moving right along, this is what I told you about where I like to use the alternate definition for sure, and that is a square root function. So let's just do it. The first ordered pair will come from the given x coordinate. And let's sub that in. Think about that. 7 plus 2 is 9. And then the square root of 9 is 3. We're not going to use plinus here. We're just looking at that as the positive root because it's a function. F of x is the positive root of x plus 2. Okay, now the second order pair will be x comma root x plus 2. x1, y1, x2, y2. This time, you know what, this time I'm going to write my notation a little bit different because this is shown as f of x. I'm just showing you right now that you can write it like this, f prime at 7. So don't just call f prime of x. We will get to that in the third video. But right now you need to show that you're specifically looking at a particular point here, and that's x equals 7. So put that there instead of x. All right, and let's do y2 minus y1 over x2 minus x1. All right. And I'm smiling because I just think these are fun. It's like, well, now what? What do we do? This is different than what we've seen before. Actually, if you are in my class, this should not look that different because we did work on these types of, oh my gosh, I forgot the limit. Shouldn't be smiling anymore. Limit as x approaches 7. There we go. It's there. It was always there. All right, we've worked on these types of limits, right? And we've discussed what do you do with something like this? Well, you are going to look at that numerator, root x plus 2 minus 3, and you're going to multiply both numerator and denominator by the conjugate, meaning change that minus in between these two terms to a plus. We are allowed to do that because multiplying top and bottom by the same thing is like multiplying by 1, right? This is equivalent to 1. So we're good. I'm going to put this in parentheses and this in parentheses. And if you've never done one like this, I'll give you a little pro tip here. If you're one of my students, hopefully you remember this from when we practiced these in the last chapter. What you want to do with this is you do want to actually fully multiply the two binomials in the numerator. So you're going to, FOIL here because you're trying to simplify that into something that will actually cancel with the x minus 7 in the denominator. Remember, your goal is to evaluate this limit. That means eventually, being able to sub 7 in for the x. You don't want this x minus 7 here. That's a problem. So we will be foiling in the numerator. However, you will not multiply through in the denominator. You want to keep this factor of x minus 7 here. You lose it if you actually FOIL the denominator out. You understand what I'm saying? You want to keep this here because this is a problem for us and we need to get it out of there. All right, so I'm going to take root x plus 2 times root x plus 2, and that just gives me x plus 2. I'm not going to write the next two terms. When I do my outers, 3 times root x plus 2 is positive 3 root x plus 2. Do not distribute that 3 through. And then inners is minus 3 root x plus 2, and those add to 0. Those cancel. Finally, the last, negative 3 and positive 3 is minus 9. Okay, I went through that kind of quickly. If you need to pause the video and write that work out and understand where this came from, I encourage you to do that just so that you don't feel so lost, and then come back to me. And as usual, reach out and let me know if you have questions about that. And now the cool thing happens here where positive 2 minus 9 is negative 7, right? And hopefully now you can see why I said you want to keep this x minus 7 as a factor, because these divide to 1. We have a 1 left in the numerator, and we have root x plus 2 plus 3 in the denominator, which now is a form where we can sub 7 in. So we have root 1 over root 7 plus 2 plus 3. 7 plus 2 is 9. The square root of 9 is 3. This is 1/6. We'll write this one out fully, even though it's kind of one that's difficult to, I'm like, look at your answer key and make sure the answer is a 6. It is. All right. This is called, I've been teaching for 10 years, but I'm still not confident. All right. So we're going to write this as 4 f of x equals root x plus 2 f prime at 7 equals 1/6. That's what we just found. Yay. Again, I like to use the alternate definition with square root functions. It can be done with the original. It's not that difficult. It's not actually a very different process either. It's just you have a plus h thrown in there as well, which just adds like a third term under the root that I just think is unnecessarily busy looking. Okay. So finally, in this last little part, I'm going to go over example 3. I am going to leave the problem that's underneath of it in the guided notes. There's like a little you try here. I'm going to leave that for you to try. Before I go, I will tell you the answer to that one. But what I want to talk about here, and I'm just going to briefly discuss this because we'll be seeing it again often in this chapter. So we'll talk more about it as we get there. But I want to remind you that what you are doing in all of these problems that we've been working on so far is you're finding the slope of the tangent line. Now, there will be times where you want to write the actual full equation of the tangent line, meaning like, the line itself has an equation, right? You could write that equation in like slope-intercept form, y equals mx plus b, or you could write it in point slope form. That's what we're going to do. Okay, and you'll see as we continue to study derivatives why that's helpful. Another type of line, though, that will be helpful at times is called the normal line. And so we're only going to touch on it very briefly here. I hate to do that, just like sort of throw it at you and say, here's something else. But you'll see that it's not that tricky, and we will, I promise, talk about it more as we go through this chapter and actually the next chapter. A normal line, okay, so here's a little definition for you, is a line that goes through the same point, but it's perpendicular to the tangent line. So just to give you a little visual here, how should I do this? I'll just sketch. I'm just going to sketch up here real quick. If you have the function, let's use this one, y equals 2x plus 3, that could possibly look something like this. It's a parabola, right? It's opening upward, shifted up by 3 units. And you're looking in particular at the point x equals 5, which I'm just going to say, let's pretend that's about right here. All right, the tangent line, could look like this. And the normal line, again, it's a line that is perpendicular. It goes through the same point as the tangent line, same point on the curve, but it's perpendicular. So it could look like that. And, perpendicular lines are always lines that we like to study for different reasons in mathematics. And again, we will talk more in particular, I believe it's in section 3.7 that we start to talk about light and like light going through a lens. And that's somewhere that we can see an application of when the normal line would be beneficial. But right now, we're just starting with basics of derivatives, and I need you to know that sometimes we like to see the full equation of the tangent line, and we like to write the equation of the normal line, and so that's what we're going to practice here. All right, so let's do it. Let's start with the tangent. Write the equations of the tangent and normal lines to the function f of x equals 2x squared plus 3 at x equals 5. Use either the original or alternate definition to find the slope. Now, usually at this point, I tell my students, do this. You should be able to do the slope part on your own, and you should be able to decide whether you want to use the original h approaches 0 definition or the new alternate definition as x approaches a. I am going to, just to give you one more example, I am going to set up the slope, which I will write as f prime at 5, with the alternate definition. I guess I should write my points, right? 5, comma, okay, let's think about this. 5 squared is 25, multiplied by 2, that's 50, add 3, we have 53. Second ordered pair, if I'm using the alternate definition, would be x, comma, 2x squared plus 3. If you would want to pause the video because you prefer to use the alternate or original definition and then come back to me and see if you got the same answer that I did, go for it. So we have here the limit as x approaches 5 of y2 minus y1 over x2 minus x1. And this is another one where we're going to use factoring as our manipulation technique. However, please note first that you can simplify this. Sometimes I see students trying to factor with factors of negative 53, and I'm like, what are you doing? Nope, look at this, 3 minus 53. Those are like terms. I'll put that right here. I think I can fit it. This is 2x squared minus 50 over x minus 5. Now we'll go down here. You can factor a greatest common factor of 2 out of the numerator. And then we have a difference of squares to factor in the numerator. X squared minus 25, that factors into x plus 5, x minus 5. And that does what we need it to do. So we have left 2 times the quantity x plus 5. I'm just going to bring this up because I know like right in here is my face. Or, I should do this. I'm just going to go away. That way I have all this room. Okay, sub 5 in. And that gives us a derivative of 20. Now, I'm just checking that in my head. Yep, that's good. That's what we want there. Now, I guess I also have it on a, sorry, I didn't like the way that 0 looked. I could also check with my answer key. I forget that I make answer keys. Like, they just kind of sit there. All right, here's my derivative value. We're not done with this problem. That's just the derivative. What we need to do now is write the equations of the tangent line, and then we will write the equation of the normal line. So let's just talk about for a moment how you write an equation of a line. A line, can be written in what we call slope-intercept form. It could be written in what we call point-slope form. It could be written in standard form. I don't know why you would use standard form. We don't need that here. Because we have, okay, look at this. We have a point, a nice defined point that our line goes through, and we have the slope. It would make most sense for us to write our equation of our tangent line in what we call point slope form. So if you're in my class, we have talked about this already. If you're not, here's a little quick refresher. Point slope form is, this is how I write it, y minus y1 equals m times x minus x1, where the x1, y1, that's your given point, and the m is your slope. So we will be just like filling in values for these three places in the point slope formula. So I'm going to put this down here. I'm going to say, here's the equation of my tangent line. It would be y minus 53 equals 20 times x minus 5. And you can leave the equation of the tangent line in that point slope form. My zeros always look like 6s on here. It's a 20. All right. Again, you can leave your answer in this form if you're one of my students. It's fine. It's an equation of this line, right? It's saying that this line, this tangent line, is going through the point 5, 53, and it has a slope of 20. So it gives you everything that you need. Some teachers may say, I would prefer you turn that into slope-intercept form because it's easier to work with later when we actually want to use this equation to calculate different things. Right now, I'm just like, let's keep to basics here, so we're going to leave it in that form. Now, the other thing that I know you don't really know why you're doing this right now, but it will all come together as we keep going, you just got to stick with me, is let's write the equation of the normal line. So the normal line, keep in mind, this is the cool thing when you keep your equation in slope-intercept or point slope form here. It goes to the same point. So you can start with a y minus 53. Let's leave a blank for the slope. And you can have the parentheses x minus 5. That's all still the same because you're still going through that point 5, 53 up here. Okay, the only difference is it is perpendicular to the tangent line, so it definitely does not have the same slope. And you need to know, the relationship between the slopes of perpendicular lines. So perpendicular lines have slopes that are opposite reciprocals. Opposite meaning change the sign, reciprocal meaning flip the fraction. So the slope of the normal line is negative 1 over 20. Again, you can leave your answer in that form. Oh, yay, we did it. I'll come back. Here I am. All right. So that is, that's not it. I will tell you the answer to this. However, I do want you to try to work it out on your own. And if you have questions about it, you can ask me as usual. For this U try, it says write the equations of the tangent and normal lines to the function x cubed at x equals 2. So again, I'm just going to give you those equations, and I want you to make sure that you can do the work to get there. So the equation of the tangent line is going to be y minus 8 equals 12 times x minus 2. Again, I left it in point slope form. And that would make the equation of the normal line y minus 8 equals negative 1/12 times x minus 2. Yay, okay. As usual, I hope this video was helpful. Bye.